Welcome to this session on ceramic shell molded investment casting under the course on advanced manufacturing processes. This is in continuation with the other lectures previously delivered on other advanced casting processes. In this session, we will study about the ceramic shell investment casting process. In this process, a near net shape product can be produced. This is very widely used technique nowadays. The process is based on expandable wax pattern for producing jointless molds that are required for near net shape castings. Before we start the discussion on the ceramic shell investment casting process, it is desirable to understand in brief the sequence and differences of this process from investment casting process, which we have discussed in the earlier session. Now, let us see the difference between investment casting process and the ceramic shell investment casting. The main difference between the investment casting process and the ceramic shell investment casting is that in the former process, prior to dewaxing the wax pattern, it is immersed in a refractory aggregate, whereas in the ceramic shell investment casting, a ceramic shell gets built around a tree assembly. Repeated dipping of the pattern into slurry is done to get the required thickness. The slurry is made of refractory material such as zircon with binder. After getting the required thickness of cross section, the tree assembly is dewaxed. The shell obtained is further immersed in a refractory coating and the metal is poured into it. In this process, a wax pattern or assembly is first dipped into a ceramic slurry, but for its primary coating. Thereafter, the pattern is withdrawn from the slurry and is manipulated to drain off the excess slurry to produce a uniform coating layer. The wet layer further stuccos through sprinkling the relatively coarse ceramic particles on it or by immersing it into such fluidized bed of particles. The ceramic coating is built by successive dipping and stuccoing process. This procedure is further repeated till the desired shell thickness is obtained. Upon completion, the entire assembly is placed into an autoclave or flash fire furnace at a high temperature. In order to burn out any residual wax, the shell is heated to about 982 degrees Celsius, which helps to develop a bonding of high temperature in the shell. Such molds are stored for future use, wherein they are preheated for removing the moisture from it and then molten metal can be poured into it. Now, let us see the process sequence in ceramic cell investment casting. The process sequence of ceramic cell investment casting is given in the figure 1. In this process, this first step is the construction of the die, which is followed by injection of the wax through a system like this. Then the assembly of the wax are created like this, which is then dipped into a slurry for the coating. Then it undergoes the stuccoing process, and depending on the thickness of the coating required, it is dipped in the slurry for several times, and then it is taken for dewaxing process, where the wax is removed. Now, the mold is ready for the pouring, where the molten material is poured like this, and this is followed by the cell removal process, finally gives the products like this. These steps involve manufacturing of the master pattern of wax through the master dies, then preparation of the wax blend and injecting it into the die. In the third step, the wax pattern is manufactured and assembled. It is followed by investment of wax with slurry, that is also known as coating the slurry, which is followed by drying of cell thickness, also called stuccoing process. This is followed by dewaxing of the raw molds, followed by heating and baking of the cells. This is followed by pouring of the molds with molten metal. Once the metal is solidified, the cells are removed. Then cutting off of the gates and risers are taken place to obtain the finished product. The advantages of the process are: complex shapes that are difficult to produce by other casting methods can easily be manufactured by this method. Thin cross sections and intricate shapes can be made by this process. Then finish machining is considerably reduced or almost eliminated on the castings made by the process, making it economical. The process has no metallurgical limitations. This process produces castings with excellent surface finish. Now, let us see few disadvantages of the process as well. The process is expensive process due to the cost of ceramics and the pattern, which is made of wax. As the cells are delicate, the process is limited by the size and mass obtained. Making intricate and high quality pattern increases the process cost. Let us come to the applications of this process. The process is used for making parts, those are used in aircrafts. For example, turbine blades, carburetor and fuel pump parts, cams, jet nozzles, special alloy valves, etc. The parts required in chemical industries are also produced by this process. These include impellers, pipe fittings, evaporators, mixers, etc. The parts required in tool and die making are also being produced using this process, which include milling cutters, lathe beads, forming dies, stamping dies, permanent molds, etc. and some general and industrial applications like cloth cutters, sewing machine parts, welding torches, cutter, spray nozzles, metal pumps, etc. Now, let us see the types of wax. The pattern material selection is the most important issue in the ceramic cell investment casting, also known as CSIC process. The patterns are prepared through injecting wax into the die, which we have already seen in the schematic diagram. The patterns thus made should be fracture resistant and distortion free, such that parts accuracy is maintained. The key demand for tighter tolerances from CSIC process is to calculate and control the shrinkage of pattern material in order to improve the accuracy of the products. The shrinkage characteristics of waxes and its influence on the final dimensions of casting are to be considered. The wax is of great fundamental importance in getting high quality casting, minimizing product cost and low scrap rates. Numerous factors can affect the degree to which contraction in dimension can occur while taking into account wax pattern accuracies obtained through such patterns from the die. Types of waxes and wax blend composition. 4 types of waxes, namely beeswax, paraffin wax, Carnauba wax and Montana wax, with different melting temperatures ranging from 58.2 degrees Celsius to 83.8 degrees Celsius, can be used to make the pattern suitable for use in investment and ceramic cell investment casting. The physical properties of various waxes used in this process are given in the table. The form of each of the above wax is solid at room temperatures. The recommended blend or mix of wax for the best dimensional and surface properties of the pattern are in the following ratio by weight. Paraffin is the 10%, beeswax is 6%, Montana wax 3% and Carnauba wax 1%. That is, paraffin is to bees is to Montana is to Carnauba is 10:6:3:1 ratio by weight. This table shows different waxes used in this process. These are mostly widely used waxes, namely beeswax, which appearance is white and melting point is 58.2 degrees Celsius, which gives the density in 0.97 gram per cc cubic centimeter. Then paraffin wax also appears white. Melting temperature is almost similar to that of beeswax, which is 58.5 degrees Celsius, and density is also in the similar lines, slightly less than the beeswax. This is 0.94 gram per cubic centimeter. Then carnauba wax appears black, and which has got much higher melting point in comparison to the previous two waxes, beeswax and paraffin wax. This is 81.9 degrees Celsius, and density wise also it is slightly more, that stands at 0.99 gram per centimeter cube. On the other hand, Montana wax appears brown in color, and the melting point is also the highest among these four classes of wax we have discussed, which stands at 83.8 degrees Celsius with the highest density of 1.02 gram per cc. Now, let us look into the process parameters that affects the quality of wax pattern. Like the earlier cases, to identify the process parameters, let us draw one Ishikawa cause and effect diagram as shown in figure 2. This is the cause and effect diagram given after the name of Ishikawa, in which there are four main categories of parameter. These are wax based, temperature based, dye based and time based. In wax based parameters, composition of the wax and viscosity are the most important parameters that affects the ultimate product quality. Then, as we have already spoken, temperature is one of the major parameters that should be maintained properly. Here, temperatures of the dye, temperatures during the injection, that is of the material, and the temperature of the nozzle, that can affect the product quality. Coming to the dye, the dye temperature, as I have already indicated in case of temperature based parameters. Then lubrication of the dye, that affects, then the surface of the dye, which can affect the surface of the mold or the finally the cast product, and then venting of the dye, which is responsible for escaping the gases. Then other parameters, time based parameters are very important parameter is injection time, then holding time of course, then post injection cooling and dwell time. These are the most important parameters that influences the quality of a product obtained by this CSIC process. This diagram depicts that the parameters are quality based parameters, which affects dimensional accuracy, surface roughness, mechanical and metallurgical properties. The wax patterns. The parameters of the wax pattern that affect the quality of ceramic cell investment casting are wax temperature, dye temperature, pressure and wax viscosity of course. Then Stuiko based parameters, that is the type, composition, size and size distribution. Then alloy parameters, that is pouring temperature, pouring time and type of alloy. Then regarding ceramic slurry, pH value of the slurry, density of the slurry and viscosity of the slurry are the parameters of major interest. Then mold based parameters include firing temperature and dewaxing temperature. Thus, it indicates that the following process parameters have an effect on the quality of the wax patterns with respect to dimensional accuracy and surface roughness made from the dies. Let us see the pattern die. A typical 3-step pattern used for making the mold by ceramic cell investment casting process is shown in the figure 3. A die made of aluminum is shown in the photograph in figure 4. A photograph of the wax pattern, which in turn will be removed from the die, is also shown in figure 5. This is the pattern, a 3-step pattern, and this is the aluminum die in which this 3-step mold is created, and this is the wax pattern. Now, let us see some details about the wax injection machine. A wax injector is a machine which makes use of an earlier conditioned wax and injects it into a die in order to produce a wax pattern. An injection machine was designed and fabricated at IIT Roorkee and is shown in figure 6. The machine has 3 basic components: the heating unit to maintain the temperature, the injection unit and the die clamping system. This machine has the following essential components and provisions: a jacket provided for heating and melting of the wax that occurs in an aluminum reservoir with provision for slow speed stirring, injection of the liquid wax from the brass cylinder under pressure into a closed mold, then maintaining the injected wax under pressure for a specified time to prevent the back flow of the liquid wax, then provisions to compensate for decrease in the volume of melt while solidification. Through these basic functions, the mechanical and thermal inputs of the injection equipment are coordinated in line with the basic properties and behavior of the wax under process. The injection process includes some other sub processes such as feeding of the brass cylinder through an aluminum reservoir gravimetrically, use of a control valve and controlling temperature with thermostat during the stages of melting, conditioning and injection is done in order to ensure high pattern quality. This is the schematic sketch of the wax injection machine, in which this is the nozzle and this is the wax reservoir. This is the plunger and cylinder arrangement through which this is pressurized. Other components are in the screen. A temperature control is made use of controlling the temperature during wax injection in this setup. Let us discuss few recent trends in investment casting process. The benefits of investment castings are tremendous. We can manufacture complex parts as close as to the final part as possible. This considerably reduces the costly post processing activities involved. This post processing, as far as casting is concerned, is a very costly activity. In many cases, fine features are to be created which could not be produced in the casting process, or in some cases the surface finish has to be obtained with the help of some secondary operations which we call as post processing. In some cases, the casting needs to be machined again to obtain the desired dimensions, which also falls under secondary processing or post processing. Therefore, this adds to the cost of the product, as well as this causes loss in the material, it causes tool cost, and as well as it cost in terms of time required to produce the part. All these things can be eliminated to a large extent in the investment casting process. Here very fine intricate shapes can be produced, as we see in case of fine products can be produced by using this investment casting process. Wide variety of materials can be used to produce different parts. This helps the designers to optimize different part characteristics. At the end, we get a very good surface finish with a high degree of precision, which is very important, as I have already indicated. Otherwise, we may have to go for secondary operations, some machining operations or finishing or polishing operations, which involves cost. Investment casting is a flexible process with a possibility to use large variety of materials. Due to this flexibility, it is easily suited for automation as well. Labor intensive work in the foundries tend to lower the productivity. So, this might be due to the labor unrest, labor unavailability, labor fatigue, and so on, or unavailability of the skilled labor and so on. Therefore, this situation should be brought under control, and one way to bring this or counter this is use of automation. One more factor is more dependence on labor skills creates bottlenecks in the process, because a factory can afford to a limited number of skilled persons, and the process goes to a bottleneck situation where these skilled persons are, or the intervention of these skilled persons are necessary, and thereby it makes the entire process slower or in other words, the productivity gets affected, becomes lower. Further, this leads to human errors due to fatigue, leading to low output and increase in overall cost. As we know, time can be correlated with cost. Therefore, higher the time for manufacturing or higher the lead time, higher will be the cost. Moreover, accidents are also common in traditional foundries. As we have already indicated earlier, foundry industry is an industry which is considered as labor intensive and which has got number of processes which are potentially dangerous for the workers, like it handles high load, it handles high temperature, and therefore, all this needs to be carefully controlled to avoid accidents or unwanted activities. This justifies why the automation in the casting process is necessary. As part of automation, nowadays robots are being widely used for various activities in advanced foundries, such as for dipping of wax trees of the cell in slurries, for building the special ceramic cells. This is a very monotonous job, and also health wise it is not very worker friendly. Therefore, this particular activity can be very well attributed to or assigned to robots, where this health hazard factor can be very well taken care of, apart from the monotony factor or the fatigue factor. Then another important thing is post processing applications, which is also called fettling, such as cutting, grinding, polishing. All this can be done with the use of robots, because once the pattern is fixed, once the part to be produced, cast is fixed, then the defects that will be produced will also be fixed for a particular pattern, or we can say if it is a batch 1, then for that batch. Therefore, robots can be easily programmed to remove that additional material or for getting that additional polish on the surface, etc., with this predetermined information, which can be already acquired and stored in the system. Let us quickly look at the advantages that one can derive using robots. The overall cycle time can be reduced. This is a very important factor as far as the yield of the factory is concerned. The investment put in is one time setup cost. Say for example, one robo is put in place, then it will be working for number of cycles. Therefore, overall investment per product will be much less, although the initial investment will be huge, which gets paid back over a period of time. There is an increase in about 20% of productivity and efficiency with the use of robots in these shops, which is substantial, 20% of increase in productivity. Robots can also be used in harsh environments like shot blasting areas in a foundry, wherein there is a high risk if the fine shots are inhaled inside. As we know, shot blasting is a process where generally small particles, say around 50 micron diameter or 20 micron diameter as the case would be, particles are of the materials can be cast iron materials or can be ceramics like alumina or something like that, or silicon carbide. Generally cast iron particles are also used, and these particles are used to shot blast a surface, means they are accelerated towards the surface at very high velocity, and this causes the surface to hit and induce some roughnesses. So, this can be explained like this: a plane surface being hit by these are the blasting material, these are blasting material, and this is the surface being blasted. Surface being blasted, and these particles will hit this surface and cause some deformation here, plastic deformation here, and this will ultimately eventually result in a surface something like this. So, this is, we can say, this is the shot blasted surface. These particles, these are something around, say, less than 50 micron in diameter, and they can be of, say, alumina, or they can be in some cases cast iron, etc. Now, these particles, if inhaled by any worker, that is certainly not a healthy situation, and this situation can be avoided by use of robots. Moreover, some accidents occur in foundry due to the handling of heated components or molten materials. This also we have already indicated. Foundry industry or foundry shop is a place where people will have to handle high temperature materials, that is molten materials, which could be several hundred or even in excess of 1000 degrees Celsius, which is potentially very risky situation. There is no fatigue on the part of the robot, which is a very common in case of human being. Robo behaves faithfully to all human commands. This is another important aspect where there is no question of dissent being shown by any workers once the command goes unfavorable to him. Then with the use of robot, parts are processed or handled in a negligible time. Apart from the robots, many other innovations and material handling devices are used in foundries. Some of these can be listed as follows. For example, number 1, use of automated guided vehicles, also known as AGVs, in developed foundries for in-plant transfer of goods. This is a very significant aspect of automating the shops, where a frequent transfer of parts or the cast product from one unit to another unit is to be done, or the finished cast should be transferred to the stores or something like that, or the yield of the casting should be sent for the secondary processing or the post processing that needs frequent handling. and frequent transfer of the materials, that can be done through AGVs, automated guided vehicles. Of course, there are different types of AGVs etc., that which are discussions are beyond the scope of this discussion. So, different types of, as the situation demands, the AGVs type of suitable type of AGVs can be used for transferring the material from one shop to another or from one place to another for the purpose for which it is being transported. Then use of high quality testing equipment whose sensors, when dipped in the molten metal, give an idea of the composition of the metal. This is another use of high tech equipment. By using sensory systems, we will be able to know the composition of the liquid material, that means the molten material, which is important. Sometimes the material could be toxic as well or could cause harm to the human being. This can be avoided. This provides flexibility to avoid rejections at a larger stage or at a later stage and to take appropriate actions timely. Now, let us summarize what we have discussed in this session. In the present session, we have discussed in details about the ceramic cell investment casting process. Then we have also discussed its applications and some of the recent trends in this process, including the automation aspects and use of robotics in this casting process, which can enhance the productivity in the longer run. We hope the discussion was informative and interesting. Thank you.